Hi everyone, and welcome to another session on Knapsack problems on practices with adiabatic quantum computing. So, what we will do today is solving the problem that we saw in the previous version, in the previous session. Sorry, we will do it and execute it on a D-Wave sampler. That is a local machine. So we will first shape the Kubo model, and then afterwards we will send it to a D-Wave sampler. So for this we will be solving the same problem that we had before. You already know the solution, so we did a little spoiler there, but it's uh, it's also interesting to see it and to visualize the solution and see the best solution possible and how all this works. So first of all, you need to install the requirements file. Uh, it will probably be not be uploaded as a folder. You will have separately the notebook and the requirements file in the materials, but you will have them. We will import these packages from these libraries. These ones are for declaring mathematical expressions. NumPy also. This one is for plotting. You will see it afterwards, and this one is the specific one on the way for using the simulated annealing sampler. Here I just defined our problem. We have seven investments, seven number of investment or possible investments. Let's say we have 7 companies. We have 4 slack variables. We already calculated that in the previous session. We have a Lagrange multiplier with a value of 15, and our maximum weight is 10 million. That is the maximum weight or the maximum budget for our investments. Here I'm just declaring all the variables. So for x, we will have x sub 0 until s x through x sub 6, sorry, and with the slacks something similar. We will have s0 to s4, s3. We will have 4 slack variables, and all binary variables. This will be helpful afterwards to have all of them. And these are the profits, these are the weights, and the scale factors. Remember that we will rescale all the numbers for the problem to be a bit more easy to manage and to visualize. So let's jump to defining the Hamiltonian. Hamiltonian will be I will just be applying the formulas that we got before. So it's sum of profits, each of the profits multiplied by the variable divided by the scale factor. For each of them in number of investments. So for all the companies, let's say. And we will also have here plus alpha, that is the Lagrange multiplier, multiplied by let's put here an integer maximum weight, and we divide it by the scale factor, minus this is only the W that we had before, and then we have sum of weights, so I multiplied by x sub I, divided of course again by the weights scale factor, and all of these for, remember that this is summed for all of the companies. So we'll have here is just the mathematical expression that we had before, and we need to add also the slack variables that are minus S0 minus, with their coefficients that we already know, S1 minus 4 S2 minus 3 S3. And this part is all powered, it's all squared. So we have here, let's just print it so we have an idea of what this looks like. So this one, oh, sorry, I need to, did I run? No, yeah, I need to run this first. 3 seconds, something like that. 5. And then now I can execute this. So yeah, we have, as you see, all the Hamiltonian. Try to have all the profit part, and then we have the alpha multiplying all the weight part that is squared. So what we will do now is, because we have this squared and we want all with also the quadratic part, because we want to construct the cubo, then what we will do is expand, just expand the edge, the Hamiltonian. Let's just print it. So here, as you see, we already have the quadratic terms. So we expanded all the Hamiltonian. This is such a long mathematical expression. So let's just go for the cubo formulation. That is, it will be a dictionary. Okay, so we need to convert it to a cubo that the D-wave sampler will understand. So that way we need to construct a dictionary. Here we will have for each, let's call it monomial, in the arcs of H. We won't have any coefficient for the moment. We will just declare it. Okay. The final dictionary will use tuples as keys. So let's just declare for now key as a list. And we will declare them like this because the list will evolve, and when we have it ready, we will declare it as tuples. Okay, so we will get for each. Let's skip here. For each variable in monomial.args, we will divide these on linear terms, squared binary variables, and constant coefficients. So for linear terms, we will have we will need, if this instance, of course the variable is a symbol, and variable in just to check that it's in all binary variables. That is the list that we created here, all binary variables that has all our variables. So if we have both of them, then we append, let's append it as a string. Okay, Then let's go for at least this instance. These are the squared ones. Variable powered and variable dot args dot args 0 in all, because here we have two all binary variables. Then we will key append string. We will append those variables as strings again. And then for the constant coefficients is another case, that is if its instance integer, so this is a normal coefficient, then coefficient will be the variable. So we just got here. What we will do now is for the Kubo to get it, we will remake the keys to be tuples, as we said before. So in the after these for loop, what we will do is just converting. If we have these as one, what we will do is key equals key plus key. So these ones we will also have a tuple, but key equals tuple key for the ones that only have one of them. But if the length of key is equal to 2, so for those that have two of them, if key not in, so if we still don't have it in our Kubo formulation, then the key the value for that part in the Kubo, so the value for that specific key will be, as we didn't declare it as an integer, it will probably have some decimals. It can, so we will get the coefficient just in case. I'm thinking I would maybe deleting that part here, but no. Else, yeah, Kubo. Okay, we will do the same. If this is in the Kubo, so we already have that term. What we need to do is just sum everything. So we are just summing, for example, 2x0 x1 plus 2x0 x1. What we will have is 4x0 x1. So we will just need to just this, add the coefficient, and then let's just print this so we know what we are talking about. So this is what I'm talking about here. We will have these kind of tuples that are the ones that we added here with their coefficient in a float. So as you see, well, all of them have a decimal of 0 because we declared them as integers before. But yeah, let's just continue with this just in case you have other kinds of coefficients and you want to try it. And then afterwards, after all the ones that are the same, we will have the ones that are different and their coefficient also. Okay, so this is the way that a Kubo is formulated to get it into a sampler. Now we defined our problem, our Hamiltonian, we expanded it, we have the Kubo formulation, so let's try to execute it. So sampler equal simulated annealing sampler, of course. Number of reads, it's equal to, for example, 5,000. This is you can try with other numbers, but this is the usual one that I normally use. Response equals to sampler dot sample cubo cubo numbers. Let's just delete this part. Let's keep it simple. So this is the number of reads, and we are sampling the cubo. Okay, and we will aggregate this. Okay, so for printing this, let's just do for values and another a placeholder for a value that won't be really used, and number of occurrences in response.data. I don't need all that copilot, thank you. We will define variables as the key for key in values if values key is not zero. So what we are doing here is the variables will only be the ones that don't have a zero. So only the ones that will be taken into account in each of the solutions. So response will have all the solutions for all the reads. So 5,000 solutions. Some of them may be repeated. Some of them will be repeated. And the one that will be the most repeated is the best solution. Is the global minima. So what we are doing here is, okay, show me for each of those solutions. So the solution for read 1, read 2, read 3, etc. For all of them, just show me the variables that are not zero. So just show me the companies where I am investing. Do not show me the ones that I am not investing. So we can print it. Let's print it in a normal way. So no decimal numbers here. But we will probably have these. What I'm trying to do here is the occurrences. So I'm printing the occurrences and the solution. Okay, you will see it in a moment. So this will be dot format, and then so what we will be getting is the number of occurrences divided by the number of reads. So how many of the reads were the times that we got this solution, and the solution that will be the variables where we are investing. So we will get replacement for out of range for positional. Sorry, I missed this one. Okay, so these are all the occurrences with all the slacks and everything. So we should, for getting the best solution, let's just print the best solution without all that noise that we have there. As you see, there are occurrences that have so much, and there are some occurrences that only happen once in all the reads. So for getting the best solution, let's go for let's declare the best solution. Yeah, let's Okay, so as we will be looping, I think this is smart that creating this as -1 because we will be looping in values, the other occurrences in response data. And then here, what we will be doing is comparing all of them. So if number of occurrences is larger than best solution occurrences, we will have best solution values and best solution occurrences number of occurrences. So we will be ranking them. So if the number of occurrences is bigger than the one that we have as the best one, we will replace it. We will replace the values and we will also replace the occurrences. And for the next one, it will be aiming to be larger than this one again. That's why we needed the -1 there for the first of the times that the loop executes that do not have the occurrences will at least be 0. So we will have it in the first run. So for best, now that we have the best solution, let's declare the best solution variables. What we want here is key for key in best solution, but let's do not show them if best solution key is not 0 as we did before, so we are only showing the one that we are investing on, and key x sub. So what we will be doing here is just showing all the variables that we are investing on in that form. Okay, so let's just print it. So for printing it, print best solution. We will do it. I'll make it more visual just for you. If you just go through the Jupyter notebook, just for you to be clear and all those things. So best solution will be, we will be doing again is, so one decimal for the percentage, and we will format these. I lost this one. Okay, as so we will have here, we will have the percentage of the times that it occurred. So best solution occurrences divided by number of reads, and then we will have the variables. So what we will have here is the percentage of occurrences from all the occurrences from the 5,000, and we will also have the variables where we are investing. If we did everything right and the sampler is working all right, we will have the solution here that we got in the previous session. So that means we will have, with whatever percentage, we will be investing in the company 0, 1, 5, and 6. Let's see. Okay, magic. No, it's not magic, but it's quantum. But we have 14.6 of the total occurrences were on this solution. That is the solution that we got the most. So yeah, this is working great. We got to the solution that we wanted. So let's check the constraints in case you want to explore a bit on this and change the profits, the weights, and everything. You will have already the code for checking all the constraints. So for the best solution weights, let's go for weight. I'm thinking, okay, for key invest solution variables, and then here total weight equals the sum of all the best solution weights. So what we are declaring this here is I'm just getting all the weights that we for all the investments that we did. So for all the variables that we are investing in, remember that we selected only the ones that got a 1. So we only the ones that we are investing. I'm getting the weights, and I'm calculating the total weight of what we are investing. So the total amount of money that we are investing, to compare it to the total budget and see if we are surpassing it or not. So let's just print our total investment. Total investment. As we did before, we will do it with a simple format. And let's just put here if it's okay or not. So just by looking to the result, we know if something went wrong. So first of all, we will have the total weight. Then we will have the maximum weight that we already defined, and then put something like okay if total weight is less than max weight, else error. Okay. I forgot here the dot format. So yeah. Okay, so this will be the total investment. Let's see what we invested also in all of this. So for key, like the distribution of wastes. So for key in resolution variables, print format key. Okay, let's do it in another way. Sorry, Copilot. So we will print something like this, but let's define here asset ID. That is print key 2. That's the one. And then we will have key here, key, and wait for each of the asset type bits. So for each of the asset IDs, or the for 0, 1, 5, and 6, we will have each of the weights. And we can also calculate print. That's something like that. No. Print. Let's leave a blank line here. Cash dot format as always, and this will be the maximum. This will be the amount of money that we have in our pocket, so that we didn't invest. So maximum weight minus total weight, that is what we invested. So this is okay. We're investing 9 million. Our budget was 10 million, and these are the investments. So this is the distribution of those 9 million. So we will have 1 million in cash. So we are not surpassing our budget. So the first cost rate is perfect. So let's now calculate the expected return to see how much money are we getting. Um, this is the same way as we did with the weights. So we first declare the best solution profit as we did with the weights. This will be something similar. Actually, I can just do something similar here. Copy this. Let's just copy and start changing. So best solution profit will be, this is not a good practice, but it's just for you to not lose so much time. Profits is profits here. We will do the same for key in best solution variables. Total profit will be the sum of best solution profits. Okay, so we are getting all the profits, and then we are summing up the total profit. So total expected profit will be here. We should change this. So let's just delete this. So total expected profit, let's put it like this, and also the percentage. So we can put here 0.1. Let's leave one decimal number for the percentage, and the percentage. Then dot format, and we need to fill all those blank spaces. So for the first one, it will just be total profit, and for the second one, it will be just this. So the percentage of the total profit, that is the sorry, this is not max. This is divided by the total weight, so the total that we invested. Then for key invest solution variables, we'll have the definition of asset ID again. This we won't need it. And here let's have it like, let's split this and start from the beginning. So let's have it like this. Okay, let's have here, as we did before, the percentage. So this would be 1 decimal and the percentage, and in the format we would have, so first of all we would have the key, second of all we will have the profits, set ID as we did before, and then we have the percentage, that is profits asset ID. No, this is divided by the weight, the specific weight. So weights asset ID. So it's the profit divided by what we invested on it. So this way we will have the variable, then the total amount that we got from it, and then the percentage that we got. And this is the total expected profit is all of this. So 780,000 units. I don't remember if it was euros or dollars. If we want to just for having the whole visualization part, let's draw a pie chart as the one that we had in the deck, in the slides. So let's define, this is why we needed also an NumPy. So we will make an array of best. Let's add the solution and the cash. So we should do like best solution weights plus the maximum weight minus the total weight. Okay. And then pi plot dot pi, oh, pi here, pi plot dot pi y labels equal best solution variables, and then we will add the cache. Yeah, of course, that's it. Okay, and then we can just do this is just something that I usually add. You don't have to add it. It's just for it to be a bit more pretty, let's say. So 1.1. This is for the percentages. So we will leave one decimal number also here. And then so we got this here. Then pi plot GCA add let's add a circle that is centered on 0, 0, that has, for example, 0.70 of a radius, and so this way we have like a better pie chart with not all the pie. And let's just show it. Let's not do anything more. Pie plot dot show. So this is our distribution. This is good for portfolio optimization techniques for visualizing them afterwards. Especially if you're you need to take that for someone that is not technical. They prefer something like this pie chart better than a dictionary or whatever formulation. So this is the way of visualizing it. Instead of x sub 0, x sub 1, you have the names of the companies, the percentage of the investment that we got, and the percentage that we didn't invest, so we still have it in cash. So I will start writing a bit what we are doing here in case you only want to go through the Jupyter notebook, or you want to go through the Jupyter notebook with the steps a bit more explained without getting to the specific minute of this video. It's probable that some of the not the distributions, but as I will be executing these again, maybe these, for example, this value here, 14.6 varies, and I get 13.8 or 15, something like that. It varies a little. It may vary from one execution to another. Not all the 5,000 reads will be the same all the time, so you can expect that. But the overall solution will be this one because it's the best one. So yeah, everything else should be the same. This distribution should be the same, and this distribution should be the same. So the solution should be the same. So yeah, now that we saw how to implement one solution in code for the portfolio optimization representing a binary knapsack problem, we will jump straight forward to the quadratic knapsack problems. We already saw a bit in those sessions, but those previous sessions, but let's jump to it in the theoretical part with some slides in the next session. So thank you for watching this, and happy to solve any doubts that you have. You can always, as I always say, you can reach me, and we can solve anything that troubles you.